Let's start the analysis of class E circuit that we have seen before. We have discussed the operation of class E amplifier. To describe the analysis analytically in terms of the nodal equations, we will assume that the switching resistance of the JFET is zero. Okay, it's not small, but it is zero. Okay, and afterwards, for the estimation of efficiency, we can assume that for low loss R is small as compared to the load resistance. So for now, let's keep R equal to zero. So over here, we have a short circuit. Okay, this R is zero, so we have a short circuit. Now, as you can see, when the switch closes, this node which is V1T, okay, so it's the same node over here. This node is V1T, and this is equal to 0, okay, this is equal to 0. So this, you can see there are pulsating zeros, okay. Zeros are repeating when the switch is closed. So this happens when the switch is closed or JFET is on, okay. So we can say the transistor is on over here, or the switch is closed. Let me indicate this by on. Okay, so V1T is 0 if your transistor is on. Okay, if it is on, and it is pulsating with approximately an amplitude of 2 VDC, as we have discussed before, when the switch is off. Okay, so when the switch is off, you see in this state, when the switch is open, we have the pulses in between on the other cycle, on the other half of the cycle. So when it is on, the capacitor shorts out. When it is off, so when it is off, we have the amplitude of pulses about 2 VDC. Why we have the amplitude of 2 VDC? We have talked about this before. Since you see, once the switch closes, you pump the energy into the RF choke. Okay, the inductor L1 gets it stores energy into its magnetic field. Once the switch is open, no current flows through this node. The inductor, the RF choke, then provides energy to the rest of the circuit. Okay, so it provides energy to the rest of the circuit, and the energy stored by the L1 once the switch was closed was equivalent to the supply voltage VDC. Okay, so it supplies an equivalent voltage of VDC. So you have an amplitude of 2 VDC. Okay, because it is an offset of VDC. At DC, since there is no drop at the DC drop across L1 is 0. Okay, so already your the drain of the JFET is already set to VDC. So you have VDC offset over here, and once the inductor starts providing the energy, once the switch opens to the rest of the circuit, the amplitude reaches to VDC. Okay, so so we have assumed that the JFET is short. The on resistance once the JFET conducts R is 0. So we assume the opening and closing of switch to be dictated by let's say a sine function. Okay, so the switch will be open whenever sine omega t is positive. Okay, that it means it opens at, let's say, t equal to 0. All right, and then it closes at the other half cycle. So for example, if you switching is like this. Okay, so let's say at t equal to 0, your transistor is off. Okay, or the switch closes, so transistor is off. Switch closes, it is open, so the transistor is off. Okay, it's not conducting. And then at omega t equal to pi, so this is omega t, and then I multiply this by, so this is omega t equal to pi. After the half cycle, the transistor is on. Okay, switch closes, so the transistor is on. Switch closes, so transistor starts conducting. Now this trend continues. Okay, now assuming a very high Q of the series L2C2, so what it says is that the combination of this series LC circuit, it is a very high Q. The Q given for a series RLC circuit is given as omega times L2 divided by RL for this circuit, divided by RL. Now, if it is very high, suppose this is equal to or greater than or equal to, let's say 10, a very high Q value. So that you have a perfect sine wave. Okay, whatever the resonance frequency is, it will set a output to a single frequency or tone. So without any compromise in the amplitude, we can have a nearly close to a nice looking sinusoidal pattern. Okay, with a frequency and with the same amplitude for all time. So if it is a very high Q circuit, or it provides high enough energy storage, so there is no damping. So let's say we have a constant V out peak. Okay, so V out peak and minus V out peaks. So we have a sine wave output at the load if we assume a very high Q. So assuming high Q of a series combination L2C2, we use a simplifying assumption that the load voltage is a perfect sine wave, and we express this load voltage VRL as V out peak of T sine omega T plus phi, where phi is the phase shift to be determined. Okay, we are going to determine the phase shift. Now, assuming for a high Q RLC circuit, we assume a sinusoidal output. So the current into the load is given by the division of, so this is actually VRL over RL. So that's the expression. The load current is again sinusoidal. Okay. So by inspection of class E amplifier circuit, you can immediately write an equation for the current through the capacitor C1. So let's see where the C1 is. You see, this is where the C1 is, and once the switch is open, so what is going on over here is once the switch is open, that means C1 is not shorted out. Okay, so you are having a current IDC through L1 through the choke. We have IDC. So the thing is, we have IDC and minus. Let's call this current. So this is a series current. So whatever the current is that flows through the load, flows through the LC series circuit. Let's call this current IRL. Okay, and we have seen that IRL is sinusoidal for a very high Q LC circuit. So IDC minus IRL is equal to the current through the capacitor, right? So IDC, if you apply Kirchhoff, you apply KCL over here, Kirchhoff current law, so that is IDC minus this current is going to give you IC1. Okay, so this is IC1. And in terms of the node voltage, if you so wish to express this, it's not hard to see that this is equal to C1 d1 by dt. Okay, so that's your first equation for the current through the capacitor when the capacitor is not shorted out, or when once the switch is open. Okay, it means the transistor is not conducting. So let's see, we have this equation over here. This is IC1 expressed in terms of the node voltage V1, C1 d1 by dt, that is IDC, and this is your IRL, what you have seen before. This is sinusoidal. Okay, so IDC minus IRL gives you the current through the capacitor C1. Okay, the shunt capacitor C1. So if you impose the condition that since we are switching the transistor on and off, so for example at omega t equal to 0, the switch is open, so the transistor is off, and then once the switch closes after omega t equal to pi, switch is on. So if you are imposing this condition such that IC1 is 0 at omega t equal to pi, so you see what happened at omega t equal to pi is that the switch is closed. The switch is closed. So we have IC1 equal to 0, right? Because once the switch closes, you are shorting out this capacitor. And IC1 becomes equal to, this is a short circuit, right? So this is shorted out all the current all the current flows through the transistor, okay, once the switch is closed. So IC1 is 0 over here. We assume that the negligible current flows through the capacitor, okay, it doesn't need to flow through the capacitor, it flows through the short circuit shunt branch once the switch closes, right? So exactly that is what is happening. Supposing the condition that IC1 is 0, IC1 is 0, okay, so what we have said over here, IC1 is 0 once the switch closes. At omega equal to phi, we assume that we find that sine phi is given by this expression. Okay, how is this coming out? You look at this expression. If you are going to replace this by pi, and that is the instant once the switch closes. That's instant when the switch closes, omega t equal to pi. The expression becomes like you have IDC minus V out peak over RL. So we have this expression, V out peak over RL. That's my load current at the point once the switch closes. All right. So let's see what this is. I know that IC1 is 0. Okay. So I'll just equate the right hand side to 0. But before that, we have sine pi plus phi, okay, sine pi plus phi, okay. Sine plus phi, and that's the close of the argument, and then the right hand side is 0, right? So what is sine pi plus phi? You see that this is sine, let's expand this, sine pi cosine phi, sine pi cosine phi plus cosine of phi, which is minus 1, okay, sine phi, sine of phi, sine phi. And what is this equal to? This equals to minus sine phi, okay? This is minus sine phi. Why? Because the first term is 0. The first term is 0. Why it is 0? Because we have a sine pi over there. You can see, okay? So the first term is 0, and you're left with the second term. So that's what you get, right? If you simplify this expression, you see what you get over here is IDC. So instead of a minus, I have a plus. Because of the minus sign over here, it becomes plus V out peak. That's my amplitude of the voltage at the load divided by RL sine phi. Okay, that's it. That's my switching constraint. Because that happens, the switch closes at omega t equal to pi. That's the other half cycle, and that is equal to 0. So if you want to evaluate phi, you want to make sine phi the subject of this formulation, you can see that you can write this down as minus IDC RL over V out peak, okay? That can be seen from this expression. So that's minus IDC RL over V out peak. Okay, that's what you get. So if you integrate the equation of IC1, which we have seen before, if you integrate this equation, what you're going to get is, for example, if you were going to integrate this differential over here, and then you continue this integration on the right hand side as well. You take this C1, maybe this C1 on the right hand side, 1 over C1, so you divide this by 1 over C1. So what you get on the left hand side is not IC1, this becomes V1T. So that's your node voltage. That, if you recall, this node voltage is pulsating. So that's precisely your V1T over here. Okay, so it's pulsating like this with the constant that at omega t equal to pi the switch closes. Okay, omega t equal to pi the switch closes, omega t equal to 0 the switch is open. Okay, so if you integrate this to get V1t, the voltage on the capacitor, while the switch is open, you have to keep the switch open for this integration, because otherwise, if you're going to close the switch, you're going to short out the capacitor C1. You don't want that. Okay, we don't want V1 equal to 0. So, so what you do is you keep the switch open, you integrate this, and you have this expression for the node voltage. Okay, as you can see from here, there are two terms. Okay, so if you're going to integrate this with respect to t, you have IDCT, then from sine it will become cosine with omega in the denominator, and there's a third term as well over here. So where does this term come from? This is an integration constant. Okay, this is an integration constant. The imposition of this constant is such that you see the last term is integration constant, and this is added. And this is added why? Because we have the condition that V1 of 0 is 0, and that is imposed by the switch having been in its closed state before t equal to 0. Okay, so before t equal to 0, the switch is closed, and if the switch is closed, then that means V1t is 0. Okay, so that means V1 of 0. Okay, 0 or before that, before the time 0 is 0, right? If you see over here, you replace this with 0. Replace this with 0. If you replace this with 0, then this term is going to cancel out with this term. Okay, there's a minus over here, and since this t is 0, this term also is 0. Okay, at time t equal to 0, this term is 0. So what you're left with is 0, right? This happens when your t is 0 or t is less than 0. Okay, so t equal to 0, the switch closes, right? T equal to 0 or before t equal to 0, the switch having been in its closed state, right? So V1t is 0. So next, imposing the condition that V1 be 0 at omega t equal to pi. Then from the above equation, V1t, if you're going to again express this in terms of if you make this omega t as pi instead of 0, okay, and replace this t by pi over omega. Replace this t by pi over omega, and if you do this, then cosine pi plus phi is minus cosine phi, right? So you can combine these two terms. You can combine these two terms to produce the second term, which is, okay, so first term is IDC. Your t is, what is t? T is from here, t is pi over omega. So you have pi over omega, IDC pi over omega. Then minus, we have minus, because this is a minus over here, cosine pi plus phi is minus cosine phi. So we have minus twice V out peak to V out peak over RL, omega times RL. So we have this omega times RL, and what is V1? Since V1 is 0, so let's substitute the right hand equal to 0. I'm missing one thing, that you will have a cosine phi as well. Okay, so you can make a cosine phi as a subject of this formulation, and you can end up in the result like this. Okay. Okay, so you see that there is no omega. You can cancel out this omega from both sides. There is no omega over here, and this thing comes out to be, if you take this on the right hand side, then this is IDCRL, which you can see over here, IDCRL over V out peak, all right, and then there's a pi over 2. So there is pi and there is 2. So you can make this equation in the form that looks like this. So you have cosine phi, sine phi. How do you determine the phase phi? Is that you combine both of the cosine and sine function using the identity that cosine square and sine square addition of them is +1. So if you assume that V out over IDCRL is A, and sine phi is, because you look at this term, you can see that this is equal to minus 1 over A. Okay, so reciprocal of this term. So minus 1 over A. I can write this as minus 1 over A. right? And how can I write this? This is pi over 2 in terms of A, which is pi over 2A, okay? Because this is the reciprocal IDC RL over V out peak is 1 over A, because, okay? And now if you're going to combine them, what you're going to have is pi square by 4 A square, that's my cosine square, plus sine square, that is 1 over A square, and if you can guess the right hand side, well, that's equal to 1, okay, because that's your sine. This time is sine, this time is cosine. So A is given as square root of, you see, this thing, okay. So you have this over here as well. You have pi square over 4 plus 1. So, this is basically the evaluation of the term phase phi, based on the constraint that the switch is closed at omega t equal to pi. Before and at equal to 0, it's open. Okay, so this is the condition that we have. Based on this condition, we have found out what is phi. Okay, what is phi? The phase phi. Now, from this point onwards, what remains is that we need to express V1t and the load current as the complex constants times Ej omega t. Now, since the active voltage and the current are, of course, the real parts, for example, if you calculate the ratio, which ratio? If you have a V1t over the load current, I1t, then that gives you Z. Basically, this is equal to V1t over V1t over the load current IRLT. Isn't that right? Because you see, if you look at the circuit, so this ratio must be equal to the complex impedance looking into the L2 C2 RL series circuit. So over here, if you see, you have this series circuit. Okay, this node voltage is V1t, and the current that is flowing in this series circuit is IRL. So the ratio of V1t to IRLT over here gives you the ratio of IRLT gives you the impedance Z seen looking into the RLC circuit, and that is equal to J omega L2 plus 1 over J omega C2 plus RL, right? So that's what you have over here. So Z is RL plus J omega L2. If you take J in the numerator, it's minus, so minus 1 over omega C2. So that's your V1 T over IRLT. So the load current, if you express this, that's the sine function, which the phase, since we have determined the phase, that can be expressed in terms of the constant A. Okay, so A times IDC, if you recall, is nothing but V out peak over IDC over RL. So you're going to multiply IDC by A. That gives you A times IDC is V peak over RL. So again, you have this load current in a sinusoidal form. This corresponds to the corresponding complex current can be written as minus J AIDC E J omega T plus phi U. So the complex form is nothing but you keep the cosine and sines. Again, if you take the real part of this current, which is the complex, the real part is again the sine part, right? The real part is again the sine part. So that's your real load current. So since the voltage V1t is not a sine wave, okay, so you see this node voltage is not a pure sine wave, it consists of harmonics, all right. So what you do is, for example, for the fundamental, you evaluate the fundamental tone from the Fourier component of the fundamental tone can be evaluated by the integration. Okay, so we can find the complex representation of its fundamental Fourier component by evaluating the integral. So the complex of V1t is 2 over tau. So we take the integration over half the integration, half the integral where v1t is not 0 half the cycle. v1t e minus j omega t dt gives you the fundamental Fourier component, okay, fundamental frequency, and then the complex of this. So that is again multiplied by e j omega t as we have done before, okay, as we have done before over here as well for the complex. So what we are doing is we are looking into the complex representation of the load current and the complex representation of the node voltage V1T, and the ratio of V1T to IRLT is Z. So note that by integrating over only the first half cycle, we account for the fact that the closed switch forces V1T to 0 during the second half cycle. Okay. So the switch closes, and when the transistor is on during the second half cycle, we have we have the closed switch, right? So the transistor is conducting. So V1T is 0. So we can rewrite V1T in terms of A and DC. So you see, you have the terms V out peak, for example, omega over RL. You can write this as A over omega, this term for the first term, A over omega. Then you can see that for the second term you have, again, this is the same term, so again A over omega. So what we are doing is we have expressed V1T in terms of A, constant A. Okay, we can take IDC out by expressing this in terms of A. Then evaluating the integral in equation for the fundamental Fourier component, and setting the ratio of the complex V1T to complex I1T equal to the impedance. If you carry out some algebra, you can find the two equations that can give you C1 and C2. So for example, if you are going to design a class E amplifier, you have these two equations. So if you are going to set the complex, you have the this complex V1T over I1T, okay, IRLT, so let's say IRLT, and this whole thing is complex, right? So this is complex. Well, the right hand side is nothing but the impedance of the series RLC circuit Z. Okay, if you're going to compare this with Z, in Z you have this C2, you have L2. Okay, so you can find, and this you have C1 in, for example, in V1. So if you make, for example, C1 as a formulation of the equation, you can work out this. You can do some algebra to have this equations for C1 and C2 separately in terms of L2 and C1, or in terms of RL. Okay, basically these are the design equations. I suggest you carry out this algebra to show that this is the case. Okay, you get these two equations from comparing the complex component of V1T to IRLT and equating the right hand side equal to Z to get those two important design equations. Where do we need these design equations? You see, if you look at the design procedure of a class E amplifier, what it says is that now we have seen that we can expect this amplifier to furnish the load with a sine wave whose amplitude is something like VDC, so the RF power output. If you are assuming that the output is a sine, then the average is VDC square over 2RL, right? And now so some of the conditions that what we have seen, if we assume that this is a sinusoid with an amplitude V out peak which is approximately equal to VDC, and this is a pure sine wave because it acts as a band pass filter, okay, to filter out a one frequency, and we also assume that the combination of LC produces a very high Q resonant circuit, so that there is no damping in the amplitude and V out peak is maintained at around VDC. Then that means your omega L2 or R should be at least or greater than 10, right? So that's your first design equation to find out L2, for example. So if you see what it says, that if you simply pick the value for L2, that will give a reasonably high Q, maybe of 10, so that the waveform of the load will be a good sine wave having minimal harmonic content. Then the first equation is that you pick a Q, that omega L2 is QRL. So you can find it you can set Q equal to 10. You know what is the load resistance. Okay, you can find L2, that gives you a very high Q, 10 or 20 or how much you set. at the required frequency omega, you can find L2. Then again you have to find the choke resistance. L1 you remember is the RF choke over here. This is your L1. Okay, so omega L1 can be equal to let's say 10 times of what you had earlier for a very high Q L2. So for a very high Q L2, you can express this as, for example, omega 10 times. Actually, this is 10 times of L2, right? Or you can say 10 times omega L2. Now, if this Q is 10, let's say this Q is 10 over here. Right, so this omega L2 is 10 RL, and if we are going to make this 100 RL, the other way to look at this is actually omega 10 times. So L1 is 10 times of L2. So it's a huge inductance compared to L2. Okay. So these are the design equations. So the first thing is you need a very high Q. For that you evaluate L2. Okay, from L2 you keep L1 10 times of L2. It's a high, it's a large RF choke. Okay, so you have L1, you have L2. You can calculate C1 from the following equation. You can calculate C1, you can calculate C2, and this C1 and C2 are where do we get these equations? So these are the equations for C1 and C2. Okay, and we have imposed some constants while evaluating the C1 and C2 through the ratio of V1 IRLT. The constants were that the switch is open at t equal to 0 and closes at omega t equal to pi. So basically this is what you have. So the only constant on the circuit that we have seen before was that V1t has fallen to 0 at tau by 2 the instant of switch closure. Then it turns out that this can be satisfied with a range of combinations of C1 and C2 that provides a way to set the output power. Okay, so if you are going to set the constant on V1t, that for the half cycle this is 0, or for the other half cycle this is pulsating. Okay, you can evaluate, you can obtain the equations of C1 and C2, a combination of C1 and C2 that can provide you with a high power. Okay, so the combinations with lower values for C1, for example, reduces the output power. So however, it is possible and beneficial to impose a second constant which will require a unique combination of C1 and C2. Okay, so the constant is the second constant is, if you set the first differential with V1t to be 0 at the instant when the switch is closed, well, if you're going to set this constant, the combination of C1 and C2 will produce an output power that is not small. Okay, so if this condition is met, the frequency of the amplifier can be shifted somewhat without seriously violating the condition that after half cycle V1 tau by 2 should be 0. So what it says is that if the differential of V1t is also 0, then in the second half cycle after tau by 2, where the V1t is 0, there could be small shift. There could be small shift in the frequency. For example, it could result something like this if the frequency is higher. Okay, but then this is not very important. It's all right. It could be a small shift in the frequency, but that would be very relevant in a very high switching times of the transistors. So, for example, at high frequencies where the transistors switching time is irrelevant, V1t will at least remain close to 0. During the switching process. And why we are doing this is why we are setting this differential to be 0 as well, is that we are looking for power. We are setting the output power that is not reduced. Okay, so we don't want to reduce output power. So for that we can set a second constant, and we can from the design equations we can find the combination C1 and C2 that gives us suitable output power with the condition that V1 tau by 2 is 0. Okay, or at least it is around 0, even if the frequency is shifted somewhat. So again, the amplitude of the output sine wave, you can see, is very near to the VDC, and we are expecting a near sinusoidal fashion output. So the power output is V out square over 2RL for a sinusoid output at the load, and that is 1.154 VDC square over 2 RL. Where do you get this 1.154? It's coming from here. If you take the square of 1.07 square, that is 1.105. Okay, so that's square of 1.07. The average current is your peak over 2 RL, and that's 0.577. If you express this V out in terms of VDC, you get this constant. Okay. Again, these design equations can be used to design a class E amplifier under the condition that for half the cycle V1T is closed. The other cycle, the half cycle when the switch closes, V1T goes to 0, and once the switch is open, we have a pulsating V1T of an average amplitude of 2 VDC.